Okay, let's look at some more properties of eigenvalues and eigenvectors, especially properties of eigenvalues. We'll talk first about the multiplicities. Now, the properties in this section have a great deal to do with the following fact. The eigenvalues of a matrix A, let me just make that clear that this is a matrix A, are the roots with multiplicities of the characteristic polynomial of A. And the characteristic polynomial of A is the determinant of this n by n matrix, which is obtained by the matrix A and subtracting lambda times I. Now practically what that means is that you take the matrix A, which I've shown here, and you subtract lambda from the diagonal entries. Right? Because I is a diagonal matrix, so lambda times I has lambda on every diagonal entry. All right, so keep this in mind as we talk about the different aspects of this chapter. First one, the degree of the characteristic polynomial. All right, so suppose that A is a square matrix of size n, then the characteristic polynomial of A, P of A, has degree n. Now he here uses induction, and I don't want to go through that, but let me just give you an idea of why that's reasonable. So let's consider for a 2 by 2 matrix. For a 2 by 2 matrix, the characteristic polynomial is going to be the determinant of A11 minus lambda. It's A22 minus lambda times A21 times A12. Okay. Now if you write this out, you're going to have the 2 by 2 formula, which is this times this minus this times this. So it's going to be A11 minus lambda times A22 minus lambda minus another term which has no lambdas. All right. So this term has no lambdas in it, so all the lambdas come from this term. Now, what's the degree of the polynomial should be equal to the degree of this term here. And what's that? Well, this has at most 1 lambda, this has at most 1 lambda, so this has degree 2. And notice that these 2 lambdas come from the diagonal entries. Every factor in the determinant is a product of elements of the matrix. So I can say that this way. The determinant of a matrix is a sum of products of entries of the matrix Now each product has n factors. And you can see that here. In the 2 by 2 case, you take the 2 diagonal entries multiplied together and subtract the 2 off-diagonal entries multiplied together. Now that's true for 2 by 2. It's also true for 3 by 3, 4 by 4, and so on. And you can see that by doing row or column expansions. But each product in the determinant has n factors, where the factors, so I can say each factor is from a different row and column of the matrix. Okay. For instance, if you look at this determinant, this A11 minus lambda is the first row, first column. Now if I cross out the first row and the first column, this is the only one that's left. And in fact, that's the other term. And if you think about the other term in the determinant, it's this term A21 times A12 with a minus sign. If I take A21, cross out this column in this row, A12 is the only thing that's left. And if you look at the determinant formula, every term in that determinant will always be the product of entries in the matrix, but those entries will all be taken from different rows and different columns. Now, suppose I take entries from this matrix here, this matrix A minus lambda I, and I consider every factor. Every factor is going to be a product of entries. How many lambdas could be in any factor? Well, the most lambdas I could get would occur if I took all the entries on the diagonal. If I take all the entries on the diagonal, I'll get a lambda from this one, lambda from the second one, lambda all the way down. There are n lambdas. So when I multiply that together, one of the terms I'm going to get is lambda to the nth. Right? So the contribution of the diagonal to the determinant is going to have a factor of lambda to the n. And every other factor in that determinant expansion has fewer factors of lambda. So I can say that this way. If you can think about it this way. And so, oops, let's see where it is. Okay. So in the determinant of a minus lambda to the n, a minus lambda I, sorry, the term which is the product of all diagonal entries will give a factor lambda to the n. Now sometimes if n is odd, it will, in the way I've written it this way, it will give me minus lambda to the n. But that doesn't matter. What we're worried about is this exponent n. So this is nth degree. And all other terms will have fewer n's. Down. All other terms will have fewer n's. Fewer lambdas, sorry, not fewer n's, fewer lambdas. Okay. So that means if you consider this determinant as a polynomial in lambda, you'll get one term with a lambda to the n, and all other terms will have lambdas to some smaller power. So that means the degree of this determinant is equal to n. Okay? Which is exactly the content of this theorem. The theorem says that the degree of lambda minus of a minus lambda I, which is the same as the characteristic polynomial, the degree is n. Okay? So he gives that proof by induction, which you can look through. But I like to look at this in a holistic way, and you can see why it's true. Okay, now, next theorem says about the number of eigenvalues of a matrix. Suppose that lambda 1 through lambda k are the distinct eigenvalues of the square matrix of A of size n, then the sum of alpha I of lambda is equal to n. What does this mean? Alpha of A is the algebraic multiplicity. Okay, so let me snip this just to explain it a little bit. What he's saying here is that the sum, go down, paste, there it is. Move it over. Let's do that again. Okay. So what this actually means is the sum of algebraic multiplicities. of the eigenvectors. All right, now, how do the algebraic multiplicities relate to the characteristic polynomial? Well, the form of the characteristic polynomial looks like this. Let's see where my mouse is. P of A is equal to lambda minus lambda 1 to the power alpha A of lambda 1 times lambda minus lambda 2 to the power alpha A of lambda 2, all the way down to lambda minus lambda n, or lambda k rather, because I don't know how many eigenvalues it has, alpha A to lambda k. All right? So the alpha denotes the number of factors corresponding to that particular eigenvalue that occur in the characteristic polynomial. So alpha is the number of times that the factor lambda minus lambda 1 appears. Okay, so you can call it the multiplicity of that root. Like, for instance, if you have the polynomial x minus 2 quantity squared, then 2 is a root with multiplicity 2. Okay. Or x minus 3 to the 4th, then 3 would be a root with multiplicity 4. Now, if you add up all these exponents, what do you get? Well, we know that P of A has degree n, so it starts out with lambda to the n. Okay? So there must be n terms altogether. But the total number of terms is the sum of these alphas. So that's where you're getting this result here. This is just a result that tells you about the order, the degree of the characteristic polynomial. You're just counting it up two different ways. One is we know the degree is n, and the other way is that we know that the degree can be obtained as the sum of the degrees of these individual factors. Okay, so all of this comes from the fact of the characteristic polynomial and looking how it relates to the eigenvalues. Okay. All right, so multiplicities of n eigenvalue. Suppose that A is a square matrix of size n and lambda is an eigenvalue, then 1 is less than or equal to, this is the geometric multiplicity of the eigenvalue. That's less than or equal to the algebraic multiplicity of the eigenvalue, and that's less than or equal to the size of the matrix. Now this part here we already have, because we know that the sum of the algebraic multiplicities is equal to n. Now I remind you that the geometric multiplicity is the number of linearly independent eigenvectors with eigenvalue lambda. You can also describe that as the dimension of the eigenspace. Now, we've seen cases where an eigenvalue may have 2 or 3 linearly independent eigenvectors. So the number of linearly independent eigenvectors, that is the maximum number of linearly independent eigenvectors, is equal to the geometric multiplicity, which is denoted by gamma. And it turns out that this geometric multiplicity is always less than or equal to the algebraic multiplicity. Now if you look at the proof here, it's very long and involved. So I'm going to punt on this one, and we'll just take that as a fact. You can try to read and understand that proof if you like, but for the purposes of my explanation, I'm just going to say that this turns out to be true. You can see some examples of why that's true. And maybe at some point I'll try to come up with a simple argument that shows that that's true. All right, so we'll just take that for granted. All right, and the last theorem in this section says the maximum number of eigenvalues of a matrix. If the matrix has size n, then A cannot have more than n distinct eigenvalues. And that's very clear because the characteristic polynomial has degree n. It can't have more than n roots. And each eigenvalue is a root. So you couldn't have, say, 12 eigenvalues of a 6 by 6 matrix, because all those eigenvalues would have to be roots of a 6-degree polynomial. Okay? And if you read the proof, that's the basic idea of the proof. Right, so we've seen several properties of eigenvalues that tell about the number of eigenvalues and how that relates to the size of the matrix. And that's all for this section.